Hello everyone, I'm Amit, your host for the day. I welcome you all on behalf of Edureka to this session on Hadoop basics. This session is to introduce you about Hadoop and its ecosystem. So the agenda of the session you see here, big data growth drivers, why there is so much talks. There are so many talks about big data. So we'll discuss about that. What exactly has fueled the growth of big data? Then what is big data? We will introduce Hadoop, which is at the core of big data processing. Then we will discuss about Hadoop master slave architecture. We will discuss about its core components. So then slowly we get into what exactly Hadoop framework is. So that's where we get into master slave architecture, its core components, the HDFS data blocks. You may not understand all of them as we speak now, but yes, the moment we get into all of them, you'll start making sense of all these different terms that you see on the screen now. So HDFS data blocks, this is where data gets stored. HDFS read or write mechanism. How do you store data, read data from HDFS? What is MapReduce? So once you have stored data, now you have to process data to make some sense of this data. So how do you process big data? So that's where the fundamental processing logic, which is MapReduce. Then MapReduce program we will see exact idea is you store data, now you process data using MapReduce. So we will see how you can typically write a MapReduce program. How can you typically process big data? Then MapReduce job workflow, how end-to-end a MapReduce job works. So just to let you know what MapReduce is about processing big data. It is fundamental processing framework for big data. So we will see a typical small use case and make you understand how you can process big data using MapReduce. Then we will also discuss Hadoop ecosystem and then its use cases, different use cases for Hadoop. So this is the overall agenda for this session. So let's discuss about big data growth drivers. Why big data is becoming so popular? What is that which is fueling the growth of big data? So this is what you see, tip of iceberg. Of course, not all the sources that you see here, but look at here, the social media. All of us do day in and day out. Look at these numbers. Some of these numbers, so staggering numbers. So look at some of these numbers. Facebook, every 60 seconds, a minute, per minute, how many number of posts, how a user like. And then you see YouTube, number of hours of videos every minute being posted. 300 hours worth of video every minute is being posted on YouTube. Similarly, you see number of tweets, right? 3.47 lakhs tweets per minute. Similarly, you see Instagram. So you see these are some of the social media. And then big data is not specific to any specific domain, trust me guys. Yes, a specific domain may have more availability of data as compared to other, but my experience is big data has penetrated into our lives, almost every domain. So businesses have started realizing the importance of big data, and they have started using big data processing in their day-to-day decision making. So you see, these are some of the staggering numbers here. And large numbers you see. I mean, just a minute and 300 hours of video is already uploaded. Just a minute, 3.47 lakhs tweets have been tweeted. Just a minute, and so many number of posts have been liked on Facebook. And these are the numbers which we are showing you because you and me can easily connect with these numbers. And this is what actually is fueling the growth of big data. So just to give you an instance, just to give you an example, these are some of the examples that we are aware of in our day-to-day lives. And all of them, you see here, each one of these instances of the example that we see, what exactly that is data. right? A video, that is data. A Facebook post likes, again data, and so on. Tweets, again data. So that's where a big data growth is coming across. Okay, now look at, now we have discussed that there is so much of data. Now look at some of the numbers out there. The data for the data which are expected to be out there by 2020. I mean, we are in 2020, and look at this. And also look at the steep curve here. You see the way data growth is going on from 2015. If you see 2020, it's exponential growth, right? It's not linear growth. We are looking at 53%. Compound annual growth rate, which is quite staggering, huge numbers, right? And three major trends which is actually fueling the growth of mobile data traffic. You see here, because we have more and more smarter mobile devices, defining cell network advances, 2G, 3G, 4G, even people are talking about 5G. And then you see the reviewing of tiered pricing. You have unlimited data, you have unlimited plans, and so on and so forth. So, you know, the global mobile traffic data, if you see, look at these numbers. It's huge numbers, exabytes. This is the size of data we're looking at. And also look at the steep curve from 2015 to 2020, how mobile data traffic is expected to grow. Okay, and these are staggering number, and that's where we were talking about huge data growth. Now, what is big data? Let's discuss about it. So there's, you see, as such, there is no fixed definition. What will you define as big data? But in industry, there is a common perception, there is common understanding that a data would be called as big data if it satisfies these 5 V's. Okay, if any data which satisfies these 5 V's, you can call that data as big data. Now, what big data is, so if you try to put that into definition, the big data is the term for collecting the data sets which are so large and complex that it becomes quite difficult to process using on-hand database management tools or traditional data processing systems. So please understand, you know, this is typically the definition of big data. As I told you, right, there is no uniform definition as such, but these are the parameters on which a particular data set is considered as big data. Okay, so now, so what is big data? Big data is about volume, velocity, variety, and value and veracity. Volume is about data which is quite huge, data which can't be processed using existing systems, traditional systems. So for example, typical MySQL or RDBMS Oracle system, let's say you have, but if you have data which is unstructured, like text data, like, you know, tweets data, for example, your Facebook post, you can't solve them or you can't process them using your traditional, you know, RDBMS system. Can you? You can't. So then this kind of data, right, with huge volume becomes big data. Similarly, we're talking about variety. What variety is? Different types of variety of the data. Data can be structured, data can be unstructured, data can be semi-structured. Structured, I am sure you would easily know, the data which you can fit into, let's say, row column type. The data which is typically stored in an RDBMS system. So that is structured data. Now, semi-structured would be like your XML, JSON data. That would be your semi-structured. But when it comes to unstructured, like video, audio, emails, text, tweets, Facebook post, all of that, images, that's your unstructured data. Now this kind of data where you have so much of variety, that becomes big data. Under big data, you process all of this kind of data. You don't only process structured data, which was usually the case before big data came into picture, but now you can process any kind of data, be it video, audio, image, whatever. Okay, then velocity, we are talking about huge velocities here. Velocity in the sense the rate at which data is getting generated. JSON is data format. Okay, like you have key value kind of data, it's a data format we're talking about. So velocity, the rate at which data is getting generated. Okay, so so for example, let's say real-time data processing, if you talk about. So in the banking sector, like for example, you do, you know, hundreds of thousands of transactions per second coming in, right? If it is, let's say, peak hour, you have to process that data. So the rate at which data is getting generated also, so if it is quite high, it becomes a constituent of big data. Value, that once you have data, you have to derive value out of it, right? Data in itself will not be meaningful. You have to convert data into insight. So you have to, when you say big data, right, that data which you can make sense out of it, the data where you can create value out of it, right? So that data will be classified as big data, not the junk data, of course. And then the veracity is about unambiguity in the data. Your data should be unambiguous. Data should be unbiased. Data should be truthful. So for example, let's say you want to predict the sales in next winters. Okay, you are a clothing chain and you want to predict the sales, you know, which will happen for your clothing line or your clothing business next year winter. Then what you have to ensure that you take the base as this year's winter, not this year's summer. So if you take this year's summer, then that's not right. Your data fails on veracity parameter, because that's not the right data for this problem. You got it, right? So you have to be careful about it, that you take care of the data. Unambiguous data should be there. The data should not be biased. So these are 5 different V's for big data. Now let's understand the problems of big data and why, you know, they can't be processed using the traditional systems. So look at this example, simple to traditional, you know, example, which is something which you can easily connect to. Let's say you have a restaurant, and this is how in restaurant, you know, you have the manager out there, you have the cook out there, and you have the waiter out there. Veracity would be that you have to ensure, Smita, that the data that you are using for decision making should be unambiguous, should be the right data to process. We'll discuss that, Rashmi. The tools, we'll discuss about them. Okay, so if you don't consider the right data for processing, then that will not be classified as big data. The example I gave you was, if you want to predict the sales in winter next year, then you have to take base this year's winter sales, not summer sales. Okay, so you have to have unambiguity in the data. Okay, so let's discuss about this restaurant example. So you've got restaurant, you've got manager, you got waiter, you got cook. Okay, now let's discuss how big data cannot be solved using big data processing cannot be done using traditional system. Now, Bob has opened a restaurant, a small restaurant in the city. And this is how typically it would happen in traditional scenario. So what you have, you got food shelf. Now, food shelf, you will actually, you know, cook would take in. What would happen is the cook would actually take the raw data from food shelf, will cook the data and put it in the food shelf. Okay, so it's like you are getting in data from there, and then you are cooking it out there. So this is traditional system you have. So traditional processing would be what? That you have got RDBMS system out there and you are processing the data. Very, you know, it's quite a simple scenario to understand. Traditional scenario, you got just RDBMS data, you just put in data and you can get your data processing. So the left side is the practical scenario that we are discussing, and how will you convert it into a typical technical problem. Okay, so you got single cook, you got single food shelf, you know, you just cooking in data, putting data into food shelf. Similarly here, you got the processing system, you got the storage system, so you process it just like cook processes food, processing it, putting into RDBMS. Okay, this is traditional scenario. So data is generated at a steady rate and is structured in nature, as we know, right? Because in RDBMS you got structured data. Okay, so 2 orders per hour steady rate here you have, right? You are very clear. This is how 2 orders per hour, and here if you see technical aspects of it, you processing data, you putting data into RDBMS. Now, failure of traditional systems. Now, if you see here, you know, when will this get failed? This will get failed when you can't put in data. If you see the right side, you can't put in the data into the system that you have. So the moment you start talking about the present age data, which is Facebook, you know, unstructured data. Now we know unstructured data like videos, audios, text, etc., tweets, WhatsApp chats, Instagram and YouTube and whatnot, all these data, right? Because variety comes into picture here, then it fails. You won't be able to process it using the relation systems. That's where the failure happens. Okay, so we are actually just trying to understand why big data processing is required, and that's what we are all discussing about here. Now, if you start taking online orders, 10 orders per hour, okay, you get it. And here on the right side, you see, if you start taking online data, right, the data comes in from these formats, different formats. And that's where your RDBMS fails, because you cannot process your unstructured data using RDBMS. Can you? You can't. So heterogeneous data is being generated at an alarming rate by multiple sources. So yes, it fails there. Your traditional systems won't work. As simple as that. So it doesn't work. Okay. Now, what is the issue? The issue is too many orders per hour. The solution is you hire multiple cooks. Okay, that's the solution. If you have got too much of workload, too many orders, then you should hire another cook. So this is how we'll just go about it here. So an effective solution would be that you got a lot of cooks out there. Okay, please understand, guys, all these cooks in terms of technical you know, aspects, if you consider, they are processing units. So you got processing, okay, and the food shelf is storage data. Please understand, the restaurant example, if you convert it into a technical problem, the cook would be the processing part and the food shelf would be the data parts. So all of these different cooks, they are actually processing. Processing means they are cooking food and putting into this a single food shelf data. So like you see here, data warehouse system. So you got a lot of processing units. These are all CPUs that you see here. It's just the translation of this, okay, which is the previous slide, different cooks we had. Okay, this is the restaurant use case, and here it is the technical use case. So multiple processing unit for data processing, and you got the common storage, which is data warehouse system. Okay, now the issue, what is the issue here? The issue is that bringing data to processing generates a lot of traffic overhead. What are you doing, guys, here? That you are bringing data to processing, isn't it? Because you are processing data where? In these CPUs. So data is moving out there. Data is moving from here to here. So what is happening is every time you're moving data like this. Okay, so from the common storage, data is moving to this storage unit, data is moving to this storage unit, data is moving to this processing unit. This is the storage unit. So data is moving to different processing units. So you are moving so much of data every time. Data is moving to these processing units, getting processed, then putting back into the storage system. So this is too much of overhead, because you this is too much of overhead because you are moving the data around. So the problem in this situation is, guys, that you have got processing, different processing, but all of these processing has to have data for processing, and this data will move from common storage, which is data warehouse, and this actually will result in a lot of data transfer over the network, and which will slow down your processing. This is not an effective solution. Okay, so this is the problem here. So how big data processing helps? And this is the solution. This is how big data processing. Now, what is the solution? The solution is that you got multiple stories, like you see here, multiple shells in the left side, got multiple guys working on different you see different cooks working on these different storage units. Like you see, you get this first cook gets this thing from one storage, one shelf, another takes from another shelf, and so on. So what is happening is, guys, you got different data chunks out there, and then different cooks are working on this, and finally what are you doing is you are actually mixing them up. You see here, final order is meat and sauce. If you see what each one of them helps is, let me just take the pen and make you explain this. What is happening here is, please understand, if you see here, this particular picture, this guy is doing what is, it is cooking meat, and this guy is cooking sauce. Okay, so like you see here in this phase in big data processing, what we are doing is we are actually preparing for food processing. So some of the cooks are cooking meat, some of the cooks are cooking sauce, and so on. And finally, when all of them are working parallelly, and finally once they are done with their jobs, this unit, right, what we are doing is we are mixing them up. Meat sauce, cook the meat and then cook the sauce and then mixing them up. So you know, all of that what is prepared from here comes to this layer here, it gets mixed up, and then you deliver your final order. We are actually doing it distributedly. Okay, parallelly things are happening, and then finally you are getting them together in the second reduced layer. So in MapReduce term, in big data processing term, please pay attention on this slide. In big data terms, it is called map phase and it is called reduce phase. In map phase, what you do is you work on you parallelly work on chunk of the problem. So what are you doing is you are doing you're cooking meat, you are cooking sauce, but in the reduce phase you have to finally prepare your food. So you are mixing up meat and sauce together, and that gives you the final food. So this one is for restaurant example. Exact same analogy we will take when we are discussing about big data processing, but I think this should help you understand how exactly big data processing would work. Now you got it right. This is how a map and reduce phase the big data processing works. So now we would need a framework to do that, and that framework is called Hadoop. Okay, that framework is called Hadoop. To do this distributed processing, to do this processing based on map and reduce, to also store data this way, okay, we would need a framework, the big data framework, which will help us do this, which will help us achieve this map and reduce, which will help us store and process big data, and that framework is called Hadoop framework. Okay, so this is where you have this framework. This is where you have Apache Hadoop framework. So Hadoop is the framework which will help you to store and also process data in parallel and distributed fashion. Like we saw there, we have got, you know, distributed storage, we have got couple of shelves, and then we have got distributed processing also, because there were some cooks who were doing meat cooking, there were some cooks who were doing preparing the sauce, and then finally you are mixing them up. So you have got Hadoop to process big data. Hadoop actually stores data distributedly, processes data distributedly. So now what Hadoop is, Hadoop, you see here, it has got two parts. One is on the left side, you have to store data. So that is distributedly you store data. Okay, and then right side, once you have stored data, you have to process data. So distributedly you process data as well. So that is how Hadoop is. So Hadoop is both storage and processing. The storage part is called HDFS, Hadoop Distributed File System, and the right side processing part is called MapReduce, which is the processing unit of Hadoop framework. Now let's quickly see the Hadoop architecture, how Hadoop works. Like you see here, so guys, Hadoop is basically master slave. Okay, so Apache Hadoop is the distributed storage and processing framework. Okay, now like you see here, so what you have is it is to handle big data, project manager, and then you got team members. You are assigning different tasks or jobs to these different guys. Okay, it's like distributedly you are processing, distributedly you are getting the work done. So it is master slave architecture. So got You see project manager, John, James, and then Alice and Bob. These are 4 guys who are working on the project, let's say. All right, so A, B, C, D. This is how they are working on it. Okay, let's say 4 projects. They are all working on 4 different projects, and this guy, project manager, is monitoring these 4 different projects. Okay, so the metadata is, what is metadata? Master slave architecture. If you see, the master is the manager knows the metadata is, the information with manager is, John is working on A, James on B, Bob C, Bob D. Okay, now let's say this guy, project B, is no longer being worked on. Now you see the difference, guys. What you have here is that if you have got John to work on project A and C, and project D and A, Alice, and Bob is working on separately project C and A, but project B, what is the difference here, guys? Only James was working on project B. Otherwise, for each other project, you've got some backup, you've got some copy. Okay, it's been assigned to one more person other than a single, not only one team member. There's somebody else also working on the same. But here, in case of project B, if you see here, yes, video as well you can process. Project B, if James, is not able to work any longer, then what happens is it gets failed. Okay, your project gets failed because there is no backup for B, project B. So in master slave architecture, what happens is it gets, in this situation, like you see here, if you don't have a copy for B also, it gets failed. So now let's consider the master slave architecture. In master slave architecture, you will have a master, you will have different slaves. Master will keep a tab on who is working on whom, or who is working on what, and then slaves are the actual workhorses. Slave is where the work is happening. So like in this example, these guys, 4 guys, they are the ones who are working, and the manager is monitoring them. A manager has got complete information about the slave nodes, who is working on what. Okay, that's how the master slave architecture works. Like you see here, the left side and the right side. Left side is the typical manager and subordinate use case, and on the right side you see the Hadoop architecture, the master slave architecture. You got master node and you got slave nodes. Master node would monitor slave nodes. Slave nodes is where the data gets resided and also processed. You got it? Master will have complete information about slaves though. However, the processing and the storage, so data gets stored on the slave nodes. Data also gets processed on slave nodes. So the core component of Hadoop is that you got HDFS, which is the storage part. Distributedly, you have stored the data, and then you distributedly process the data as well. Okay, in the MapReduce. So we'll discuss first about the left part, which is distributedly store the data, how data gets stored distributedly on different slaves. Now look at this. So you got here name node, you got here data node, you got here secondary name node. So you got name node, you got data node, the secondary name node, and we are talking about the HDFS component in Hadoop, that is the storage part. Now what name node and data node do, please understand. What name node and data node do, they are for the storage part. One thing is clear. So what name node does, because name node is for the master, please understand guys, name node is for the master, data node is for the slave. So what master and slave are, they are machines. We are talking about machines. Okay, HDFS is Hadoop distributed file system. So now you understand, we know there would be master, there would be slave, right? Now on master, name node is a process which will run. And what name node would do? Metadata. It will just have information about the slaves. It will have information about what is running on slaves, who is working on what is stored where. Okay, so like you see here, the information on name node would be, it will record metadata like information about data blocks, location of blocks, size of the files, permissions, hierarchies, etc. Okay, so like which file, which data is stored where, right? And which particular node has got what. So that information we are talking about, NameNode DataNode, master slave. So what is where, that information is available on NameNode. So it receives heartbeat and blocks reports from the data nodes. So NameNode is there. NameNode will continuously get complete information about the state of data nodes, and that is called heartbeat. Now this is secondary NameNode. This is actually in Hadoop 1.x. Okay, Hadoop 1.0 it is mandatory. In Hadoop 2.0 the latest version is 3.0 of course. So in 2.0 and 3.0 it's not mandatory. Okay, you can have it as an optional. It is mandatory in Hadoop 1.0 version, but what it does is it actually does the checkpointing. So what it means is that you got two files, FS image and edit log. You don't have to be really bothered about it now, because in 2.0, 3.0 it is optional. Okay, only in 1.0 it is mandatory. So what secondary NameNode does is it actually takes the checkpointing job. So FS image and edit logs, these are two files. Okay, FS image is the current state of NameNode. Please understand, FS image is the current state of NameNode. What is current state? Means once you bring in the system, once the system comes up, it will have the information about what is stored on my data nodes, okay, my slaves, what information is available. And then further on, whatever happens on the cluster, you add files, you remove files, you write files, right? It will keep adding up in the edit log. Okay, now FS image and edit log together will give me the current state of NameNode. At any given point in time, NameNode's current state will be the original state, which is FS image, and what has been changed after that, which is edit log. Got it? Right? So the FS image plus edit log will be the current state of my NameNode. And who does this? The merging of two, secondary NameNode does. Okay, so what it does is every hour by default it will keep taking FS image edit log from NameNode. NameNode does its own job because it has to do a lot of other jobs like keeping tab on the cluster data nodes, but merging them two together, FS image and edit log, secondary NameNode does it periodically every hour by default and puts the latest FS image back like you see in the arrow. Okay. So what I'm saying is FS image is the current state of NameNode. Edit log is what has been changed after that state of NameNode. Now, if I have to find out the current state, updated current state of NameNode, I have to merge these two files. Okay, FS image plus edit log, I have to merge them. So it's considered is like X plus delta X. X is my current state of NameNode when the NameNode came up. Now after that I have done so many modifications. I have edited few files, removed few files, accessed few files, changed names of files, etc, etc. What will happen is it will get accumulated in edit log, and then secondary NameNode periodically, like 1 hour by default, it will take up FS image, edit log from NameNode, merge them two together and put it back into NameNode. So it's like if you understand it, secondary NameNode is the not hot backup. Okay, it is not live backup of NameNode. It has got some information like every hour it does checkpointing, so it will have some lagged information, not exact information which NameNode would have, isn't it? So it does the merging and push back the latest FS image to NameNode. But don't worry, in 2.0, 3.0, it's not mandatory, so it's not very critical concept. Now, how the data gets stored in data nodes? Okay, sort of logs. That's right. Yeah. And now understand this. So how data gets stored? So data gets stored in blocks. So we have got blocks here, and this is how data gets stored there. Like you see here, each file stored in HDFS is in blocks. So as we discussed, there will be huge files out there, right? So huge files will get chopped off into blocks and then they will be put on different data nodes. And I told you data nodes is where data gets stored actually. Okay, so huge file in Hadoop will get chopped off. In Hadoop 2.0, default block size is 128 MB. In Hadoop 1.0, it is 64 MB. Right, so what will happen is, if you have got a huge file, let's say terabyte size file, gigabyte size file, it will first get chopped off into blocks of 128 MB, and then these blocks will get stored on different data nodes. Like you see here, if you have a 380 MB file, right, what will happen is you will chop it off into 128 MB size. So you got 128 MB, 128 MB, and the remaining is 124 MB. Because total sum is 380. So you got 3 blocks in that case. You got 3 blocks. Block 1, block 2, block 3. The last block will have 124 MB data only. Okay, like you see here on the right side, what will happen is, in your cluster, if you see, first block 128 MB, then 128 MB, and the third node has got 124 MB data. This is how data gets stored. Fault tolerance, how the fault tolerance is taken care of. So for example, let's say, guys, if you understand this case, right, let's say your file has got 3 blocks, 128, 128, 124, which is 380 MB. So this is how you will store data in Hadoop. Okay, so you will actually chop it off into different blocks and will store data like this. Now, what if any of the data node goes down? Yeah, obvious question is, because these are all machines, power failure could be there, disk can be crashed, system can be crashed. What would happen? Your file would go, right? You won't have a file at all in this scenario, because one of the portion is gone, 128 MB. Then I can't create my file again. So to take care of this scenario, look at this. Okay, how the node failure is taken care. Okay, so one of the data nodes crashed. That's what I was talking about. So like you see here, if this is the situation, if one of the data node gets crashed, you won't be able to have access to your data in that case, right? If it is the scenario, unless you handle fault tolerance. Okay, what will happen is, I won't have my data again, because 124 MB is no longer there. So to take care of this, Hadoop by default gives you this facility or capability, which is replication factor. What it means that each one of those blocks that you have in Hadoop system will get replicated by default. And by default, the replication factor in Hadoop 2.0 is 3. What does it mean? That each one of those blocks that you have got will get replicated thrice. So every single block will be available on how many nodes? How many data nodes my single block will be available? If my replication factor is 3, right? So what will I have is, in this case, my every single block will be available on 3 different nodes. Look at this. Okay, so you see here, here we have just taken a replication factor of 2. So you see here 128 MB, 128 MB I have stored twice, because look at the color coding. Okay, from that you can figure out, just for the illustration's sake, you will have one more copy. Okay, in actual world, you got 128 MB, you got 128 MB. Okay, you will have 128 MB, you have 128 MB. Each one of these will have actually one copy available in this case, but in real world, in Hadoop 2.0, you will have every single block 3 copies available. So now you understand, guys. So let's say if any of the node goes down, can I still retrieve my data? Yes, it will be, because I have already taken a copy of the data. Okay, so just like this, like we discussed, you should not put all your eggs in the same basket. So Hadoop will do it distributedly. Now HDFS write mechanism. So this is how you write blocks in HDFS. So what you do is, like you see here, if you want to, you have stored your data, right? So you have got set up your HDFS cluster. Now you want to write data. Let's say you want to write a file. Yeah, that's right, Navid. There will be 2 name nodes. One will be active, other will be standby. That's right. Now, what are you doing here is, you have got a Hadoop file. You have got a file you want to write to Hadoop cluster. Let's say. So how would you write it? Let's understand this. Okay, how do you write it? So you will actually go to NameNode, because you will say this is the client node. So client will say, I want to write a file. So you'll go to NameNode. Okay, and NameNode will tell you that you got how many blocks? A, B, and C. Okay, because file will be converted into blocks at the client side. You know very well 128 MB is the block size, so you will have number of blocks to be written. Now you go to NameNode because NameNode has got the information. Okay, NameNode has got the information what is available on which node, which particular data node has got how much disk available, and so on, right? So every single write and read has to be through NameNode. You understand this because NameNode has got metadata. Okay, so now you go to as a client, you go to NameNode, ask for, hey, you see I have this file, I've got so many blocks, 3 blocks I want to write. Can you tell me where should I go and write? Based on the information available on NameNode, it will tell you, hey, you go to data node 1, go to data node 4, go to data node 6. Now data node 1, data node 4, data node 6, they are all available on the cluster. Now what will happen is client will directly open connections with data node 1, data node 4, data node 6, and will write these blocks A, B, C, let's say, parallelly. So a connection will be made with data node 1, writing of data, that block will get started. Similarly for 4, similarly for 6. Okay, so this is writing happens parallelly. And then guys, one more thing that you should understand is that you would also have replication done. Each and every block will be replicated thrice. So what will happen in that case? Once you have written a particular block on a data node, it will get replicated internally. So this data node will replicate it to another data node, that data node will replicate it to another data node, and so on, right? So this also happens. How the switching of node happens? By core switch. This is the networking topology part, right? So this core switch will have complete information about all the switches configured there, and based on the request made, it will switch the traffic to the specific switch. Internally replication happens, right? Like you see here. So you got parallel, right? And then internally this happens. Now see the MapReduce part, okay, the processing part. Now you got your data stored, guys. Now please understand it, story of MapReduce, how distributed processing works. So let's say if you want to give somebody this problem, you know, let's say you got a book and you have to find out occurrences of Julius word in the book. Okay, so what you do is, let's say if you have to do this, what you are doing is you are asking, you know, each one of these 4 guys to tell you, hey, you see how many times Julius has come in that particular book. So you have given them book, and now what are you doing is all of these 4 are working together, but they are working separately. You see, each one of them wants to find out the number. So total hours here is 4 hours because each one of them is doing the same thing. But in distributedly, if you do like this. So what you do here is you got chapters. Chapter 1, chapter 2, chapter 3, chapter 4, let's say. And these 4 guys, you divided them 4 chapters differently. This is mapper, guys. Understand? What you have got is the bigger problem, you are divided into 4 different pieces. So you've given some of the chapter 1 to first guys, 2 to second, third, fourth. And each one of them is doing what? Finding out Julius word. Okay? So first guy says 12, second says 14, then 8, and then 11. And they just took 1 hour now because 4 of them, they are working parallelly. Okay, in 1 hour, first one tells 12, the second one 14, third 8 and 11, and then this is the map phase. Okay, this is the map phase that you are actually distributedly doing the job, and then finally the reduce phase would be what? All of them will summed up, and you'll get the answer. And you'll get the answer. All of these individual counts will go to reducer, and you will sum them up. So 1 hour plus 2 minutes. This is how it is faster. Earlier it was taking 4 hours because each one of them was doing individually. Now you have distributed it. Okay, now let's see quickly, guys, this example, typical example of a word count program. So like you see here, you have got a file. Okay, this file has got gear, beer, river, a car, river, gear, car, beer, these 3 records. Okay, the file could be quite huge, doesn't matter. Even if it is terabyte data, doesn't matter. Okay, now what happens? Understand the map phase first. Okay, so what will happen in the map phase? You will have, before map, you will have splitting blocks. data will get split into blocks. We discussed already. So the first block has got DL, BL, river, assume. Second has got this, third has got this. Then you got mapping. That is the mapper phase. So these blocks mapper will work on. Okay, so you got data stored in blocks. Now mapper will work on this. Mapper will process it. And how mapper will process? You see the processing of the mapper in this case is comma 1. So you got word comma 1, deer comma 1, beer comma 1, river comma 1. Guys, please understand what are we trying to do? We are trying to find out word count. What does it mean? My original problem is in this file, I want to find out how many times deer appeared, how many times beer appeared, how many times river appeared, and so on. To solve this using MapReduce, this is how I'm approaching. Store it first in blocks, mapping, do the word comma 1. So I'm doing deer comma 1, beer comma 1, river comma 1. Okay, like you see here. Similarly, here I'm doing car comma 1, river comma 1, then deer comma 1, car comma 1, beer comma 1. Clear? Map phase only comma 1. How reducer actually comes into picture? Look at this. Shuffling happens, and this is done automatically by the system. We don't have to do anything. This mapping code we have to write. This we don't have to. Shuffling. What shuffling will do? It will bring in all the same keys together. All the same keys means, you see, different mappers will have different keys, different words on them. They have to be brought in together first. So you see here, all beer have come together here. From here you got one beer, here from here you got one beer. So you got beer 1 comma 1. Similarly car, similarly deer, similarly river. Okay, and then reducer, what is happening is once you have got all the keys together, reducer just sums them up. So you got beer comma 2, you got car comma 3, you got deer comma 2, you got river comma 2. And that is your final answer, isn't it? That is your final answer, because this is what you wanted to do. This is what you wanted to find out. You wanted to find out the word count. And guys, even if data is huge, petabyte, terabyte size, doesn't matter. This is how it will happen. It will get divided individually, parallelly. Mapper will done. Mapper, after mapper results will get into reducer. Reducer will do its job and it will get processed. I wanted to show you, a code for this, but let me just give you the demo for this. This code, same word count problem. So this is the code for word count. Okay, the same word count problem. But just to give you very quick overview, look at this. This is the mapper code. Okay, and here we are doing this. The individual line will get converted into word comma 1, like beer comma 1, deer comma 1, river comma 1. Okay, similarly reducer code you have to write. In the reducer, this is the input as we discussed in the slide, and this is the output you get, beer comma 2, car comma 3. So for that problem that you just saw on the slide, this is the code that you have to write. Okay, this is Java code. Okay, now I'll use this code. Okay, I'll use this code and I'll process this word count file. Okay, let me just show you this file first. Now let's say this is the file that you have got, word count problem. Let's say this is the file. I want to find out, this is the text file, right guys? Unstructured data. I want to find out words count, like each one of these words, how many times it appeared. Big comma 1, data, how many times big appeared, how many times data appeared, how many times becoming appears, and so on. Using the same code which I have just shown you, what I have done is I have taken the export jar. Okay, I have exported a jar out of this code. Okay, like this. And this jar I have already placed, look at this here, in this place. Okay, this is the place I have already put this jar, word count.jar. Okay, this jar is there, and this is the file which is already there. Look at this. This is the file which I was just showing you there, right? It is the same file. Look at this. This is the file. Okay, now let me just show you the processing and then the result, how actually you can do the big data processing. This is the command that you have to write. Okay, just go here, just write this command. So Hadoop jar, this is the command. This is my word count jar, which is the jar which we have created after writing code. Okay, this is my class name. Okay, word count, this is my class name. Look at this. Same. So in this jar, I am telling Hadoop, this is my class name. This is my file path. This is my word count problem. Okay, this is my file. This is my input. Guys, understand Hadoop jar you have to write as a command. Word count dot jar is my jar. This is my class name, the class I have written. This is my input file, and I'm saying this is my output file. I want my output here. After processing, hey MapReduce, put my output here. Okay, so let me just say word count demo. Okay, let me put it this. Perfect, and I'll say enter. So you know now what we are doing is we are running that word count problem on that file, and the expectation is we should have, in this file we should have for this particular file, word count file, we should have word count problem. Okay, we should know what are the words, each one of these words have appeared how many times. You see, it is processing it. It is saying, you see here, how many times map happened, reducer happened. If you see the logs here, you will see, you see here, map 0%, reduce 0%, then map completed, then reduce completed, then the other logs, and then finally it says it is done. I've completed this. Now, how do I see the result? Just go here, the output. Okay, so this is where my result is. Just a second, where is my input? Look at this. I've already done this. Okay, just I can show you the output. Look at this. This is kind of output. Under this particular folder, which we have just wanted the output, this file gets created. Look at the output. Word count, word count, word count. Look at this. How many times account appeared? How many times address appeared? Okay, and so on. Custom cutting data. Look at this. This data appeared 118 times. This data appeared 13 times, and so on. So now you understand that what is big data, how Hadoop works, what is storage, what is processing, and how you can process unstructured data, such files like text file. It could be huge file also, guys. My code will not change. So with that, finally, I'll just show you this framework. Look at this. These are some of the tools that we cover as part of our course. So if you join us, these are the tools that we cover, and these are the Hadoop framework tools. So Flume and Scoop down, they are ingestion tools. How you bring in data into HDFS, you store data in HDFS. Yarn is the resource management layer to manage the resources of the cluster, and these are the processing layers on top. Spark, Storm, MLlib, Spark MLlib, Pig, HBase, Hive, MapReduce, and so on. Okay, so you bring in data, which is down, store the data, HDFS, Yarn is resource management, and these are different processing layer. MapReduce we have already seen here. If you see, this is MapReduce. Thank you so much, and take care.